Okay, so in this video, we'll talk about what I'll call analytical techniques for limits. And before we do that, let's think about how we've done limits before. Like say we were going to do this limit. In other videos up to this point, one way I would have done this is to make a table. All right, so you can look back at the other video and you can see lots of tables and the whole explanation for how you do limits with tables. Okay, that's a good way to learn this in the beginning, but using tables has its limitations. All right, so we need to learn like some more general techniques, a little bit more sophisticated techniques, and that's what you'll see in this video. Okay, all right, now I wanted to start with this though. Okay, so say you have this function, can you reduce it to a piecewise function? All right, okay, so piecewise function, now we've talked about those before. I've used examples in other videos with piecewise functions. Let's just not worry about what a piecewise function is. Can you just reduce this at all? All right, let's just focus on the word reduce. So this does in fact reduce. I know you've seen this kind of thing before. You could factor it, right? You could say that top part is x plus 5 times x minus 5. It's the difference of two squares. And then you could cancel the x plus 5s, and you're left with just x minus 5. But maybe you've never thought about this deeply before. Is this really equal to that? What does it even mean to say they're equal? I mean, numbers can be equal, but letters of the alphabet can't really be equal. What it would mean if this was equal to that was that when you substituted the same value of x in each one of these, that they would agree with each other. And that's not true. Okay? This will not always agree with this. So can you think of a number that you could put into this formula and you'll get an answer, and then when you put it in this one, you get a different result? That number would be negative 5. If you put negative 5 into this, you'll get 0 over 0. But if you put negative 5 into this, you'll get negative 10. And they don't agree with each other. Okay? So that's the exception to this. So we have to say, yeah, this is equal to that, but there is an exception to it. And the exception is that the x can't be negative 5. Okay? All right. How else can you see that? Well, see how we're canceling here? You cancel numbers, all right? You know, math is about numbers at the end of the day. I know we use letters, but we're using those letters to take the place of numbers that are unknown or unspecified at the moment. It's kind of like if you had 2 times 5 over 2, then yeah, you can cancel the 2's, and you can say that that's just equal to 5. Can you cancel x plus 5 over x plus 5, though? You got to think of that like it's a number. What number would you be looking at here if the x was negative 5? What number would x plus 5 and x plus 5 be? It would be a 0 and a 0. Can you cancel 0 divided by 0? You can't do that. Okay, so let's say that one thing that we may not have noticed before, but it's time to realize it now, is we only can make that cancellation if the x is not negative 5. If it was negative 5, we would be canceling a 0 over 0, and therefore we cannot get to here. Okay, so that's two ways you could see that this reduces to this as long as x is not equal to negative 5. Okay, I know that might seem strange because you're probably used to just going through the motions. You factor, you cross stuff out, you don't even think about it. But math is about numbers, and we can't take the x's for granted. They are numbers at some point. All right, so let me give my piecewise function this way. I'll say f of x is, let's see, this deal is the same thing as x minus 5, so long as you don't put in negative 5. And let's just say it's undefined if x is equal to -5. Why would I give my final answer like that? Well, because we did reduce this to x minus 5 so long as the x wasn't equal to -5. But this function, my reduced function, has to behave like that one. Okay? And what is this when the x is -5? That function right there. What is it when x is -5? 0 over 0, which is undefined. So this number for number behaves just like that. Okay? All right. So let's I also wanted to sketch the graph real quick. So let's see. What is the graph of x squared minus 25 over x plus 5? Well, let's look at it this way. We'll draw the line x minus 5, and we'll leave off this one point where x is -5. The line x minus 5 is a line that has a slope of 1 and it has a y-intercept of 5. And I'm not going to really draw my picture to scale or anything like that, but I am going to sketch it so that it gives you the right impression. Okay, so there's the line x minus 5. Let's say the y-intercept is -5 and it has a slope of 1. Okay, and then I need to leave off or make it undefined at -5. Well, if I was to draw this line right there, what point am I actually leaving off or making undefined when x is -5? Well, when x is -5, that would be -10. That's the point I need to leave off. Okay, so this open point there is going to be -10 for x and -5 for y. I have to leave it open. And now what you're looking at is the graph of f of x equals x squared minus 25 over x plus 5. When you first saw that, did you know that it was just a line with a hole in it? It was just a line with a point missing. That's all it is. How do you know it's just a line with a point missing? Because of how we reduced it. That's how. Okay? All right. So now let's say that, could you do this limit given what we've done up here? Okay, what's the limit as x goes to or approaches -5 of that? Where is y if you put your x microscopically close to -5? Imagine if you made a table and you put like -4.9 or -5.1, or it's like numbers very close to -5. They're going to take you down here on the line, right? Imagine making a table like we've done in other videos, and I put in that number, -4 point something, 9 something. It's going to give me like slightly above -10. And -5.01 or something like that, right? Something barely to the left. It's going to put me down here a little below -10. But it's going to put me close to -10, all right? So I can get that answer from my reduction up there. That's one way to do it, okay? Not the only way to do it. Like, almost anything you do in math, there's lots of different ways you can do it, but everybody should be aware of how you reduce that, why there's an exception, why it ultimately reduces to this, and these two things behave the same way, and how you can use that to solve the limit, okay? All right, so that's my first objective, is to get you to see that. Now, second objective is to show you how you could do a limit like that just by directly canceling it. Okay. Now for this one, I could reduce this to a piecewise function, just like the last one. Really, almost exactly the same. But I'll do something a little bit different. Okay. So okay. First of all, let's say just to have some perspective on this. How does this problem differ from this one? Okay, how does the limit as x approaches 3 of that function differ from the limit as x approaches 1? Well, in the previous video we learned that in this case as x approaches 1, we could plug that number in. Okay? You want to know what happens as x approaches 1 in that? We had a set of rules that said you can figure that out by putting 1 in. Okay? Look, it doesn't cause any problems for me to do that. Let's 2 up there, and that's -8, so -1/4. Okay? We can do, for this function, the limit as x approaches 1 just by plugging it in. If you made some table with some numbers extremely close to 1, you'd find the y's to be extremely close to -0.25. Now, how is this one different? If you tried to plug in the 3 in the same way as I just showed you, you wouldn't get anywhere. It would be 0 over 0. Okay? That's kind of like this one. If you try to do this limit by plugging in the -5, you'll get 0 over 0. It won't work. That's why I had to reduce it and see it this way. You know, -5 is no good, but there's still points clustering around it, right? And the arrow means it's not an equal sign. It's what happens when x is close to -5. So I can't do this limit by plugging it in. So here's the general technique for this kind of problem. Is can we reduce it? Okay. All right. So say we got 3 minus x over x squared minus 9. So okay, that does reduce by factoring. That's a difference of 2 squares, which I can factor as x plus 3, x minus 3. And then these two things cancel. It may not look like it because they're not identical. But say I factor out a -1 up here. Is -1 times x minus 3 equal to 3 minus x? It is. Okay. And then I'll look out like that. Okay. These cancel. And I'm left with -1 over x plus 3. Okay. Now what I have to tell you right now is that you can use the reduced form of this in place of that function to do this limit. Okay? So we'll reduce it, then we'll apply the limit. Okay, we'll apply the limit on the reduced form. It did not work on the original function. All right? So -1 over x plus 3. Here, if I wanted to do this limit, I can plug in the 3 with no problem. Okay? -1 over 3 plus 3, or -1 over 6. Okay, so there's the answer to the limit. Now, this might seem similar to the other one, and it is. It might be hard for you to see the difference between this and this and this at first, but what I have to say is I could have done it like this one. I could have reduced this to a piecewise function. I would have gotten a curve with a hole in it near the 3 or at the 3. And then I could have looked at the graph and saw where the hole was and found the limit that way. I could have done it. This is just a shorter, more direct way of doing what I did here. It cuts out the piecewise function in the graph, but it's really the same concept, okay? So, all right, when we encounter things like this and we can't evaluate the limit by plugging the number in, then we could attempt to reduce it and then to apply the limit on the reduced form, okay? All right, -1 over 6 is what we get. Now, this one is like the other one because what if I tried, or again, I guess maybe just to be dramatic, I'll do like this. How is this, that problem you see right there, different than this one? Well, I mean, if I want to know the limit as x approaches 1, I can just plug 1 into that and find the limit that way. I'd get 8 minus 1 over 3 minus root 1. So I would get 7 over 2. Okay, there's your limit as x approaches 1. Put in any number really close to 1, into that function, you'll get about 3.5. So that's what 7/2 is. This one can't be done that way. The 9 doesn't go in. It doesn't give you anything meaningful. Okay? All right, so here's maybe a rule that you can go by. If the limit that you start with takes the form of 0/0, then here's what we'll do. We'll reduce it algebraically, and then we'll apply the limit. This one takes the form 0/0, just like the last one. Okay? Just like the last one. Now, the way I reduce it's going to be different, but it's the same starting point. Okay? So I need to reduce this. Okay? It is 0/0 because that's what 9 does when you plug it in. And here's how you reduce it. When we have expressions with radicals, or they're called radicals, but roots, if you want to say it that way, then the trick to simplifying it that we can rely on is to multiply your initial expression by the conjugate. The conjugate is this expression where we keep everything the same, but we change that sign. So the conjugate of 3 minus root x is 3 plus root x. But the only number that we're allowed to multiply by is 1, right? If I take my problem and I multiply it by some number other than 1, it's going to be different. Obviously, if you take something and you multiply it by 2 or 3, it's different. It's not the same anymore. But this, I want you to start noticing things like this. That is 1. So I'm taking my problem, I'm multiplying by 1, and it's going to remain the same. That would be the goal, is to keep working the same problem. I don't want it to become different some point along the way. Okay, so I multiply by the conjugate down there because that will simplify the radical. I multiply it up here because I have to, because I got to keep it at 1. Okay, so here's what I'll do. To multiply these together, I'll get 9 minus x times 3 plus root x. Okay, and I'll leave that the way it is. I could FOIL these together if I wanted to, but I don't think that will help, so I'll just leave it apart. Here, look what happens. 3 times 3, that's 9. 3 times root x, that will be 3 root x. Negative root x times 3, that'll be negative 3 root x. And negative root x times positive root x, well, that will be a negative, but root x times itself is x. So you see how the conjugate simplifies the radical expression. These middle terms cancel, and I'm left with 9 minus x. So here's what I'm getting. I'm getting 9 minus x, 3 plus root x. Okay? And then down here, after all the canceling, I'm getting 9 minus x again. All right, then these cancel, and I have successfully reduced it, right? Yeah, it's reduced. It's simpler than it was when I started. That's what I mean when I say I've reduced it. Okay, so let's now apply the limit to the reduced form. So I wanted to do from the beginning, the limit as x approaches 9. But I'm going to use that. Okay. It's no problem to plug in the 9. This is, after all, defined at 9, and our rules from previous video can allow us to plug in 9 to do the limit. So I get 3 plus 9, or 3 plus root 9, so I get 6. Okay. All right. So I hope you see some similarity to the last one. We had to reduce it. We had to use some algebra. Maybe you didn't know about this conjugate that we'll use when we're dealing with roots, but now you know about it. Okay. All right. So let's look at one that's similar to this one, but it goes a little bit beyond it. So this one, yeah, it's similar. It has a root in it like the last one. It involves radicals and roots. And it says, what's the limit as delta x goes to 0? Okay, so delta x is you'll see this used a lot in math and science, and you could say that delta just in general means change. So delta x means some change in x. It represents some change in x. Things are normally changing, and in calculus we deal with the mathematics of change quite a bit. So that's what that means. Now I think if I'm working through this, delta x is kind of a cumbersome thing to write down, to be honest with you. We should all know what it means, but I'm really not looking forward to writing delta x down all the way. But it's like any other variable. It's like any other unknown. That could be y or h, or pick a letter of the alphabet, okay? So that's the way the problem may be given to me, and I understand it, but I'm going to change the notation. Okay? It would be no different if I just used a different symbol. How about the limit as h goes to 0? I think that's just as good. Okay, so limit as h goes to 0, x plus h minus root x over h. That will just be easier to write down. Okay? All right, now, could I do this limit by plugging in 0 for h? Well, what happens if you do? That will be root x minus root x. That will be 0. And that will be 0. So I can't do that. So what's this have in common with the problems that we've done up to this point? Initially, if h is 0, it takes the form 0 over 0. Okay? So what was that a cue for, that we need to reduce it? We'll find some way to algebraically reduce this, and then we'll reapply the limit. Okay? All right, so here goes. I get x plus h minus root x over h. Okay? And I multiplied this by the conjugate. Okay, so what's the conjugate of root x plus h minus root x? That'll be root x plus h plus root x. Okay? But I need to multiply by 1. So what I put down here has to be the same as what I put up there. All right? All right, so once again, this is what number? 1. The conjugate here will simplify this aspect of the problem that has roots in it. But I put it down there also because I need the number 1. That's the only number I'm allowed to work with. All right? Okay. So if I take it from here, here's what will happen. If I multiply across this way, root x plus h minus root x times root x plus h plus root x. That will be x plus h, root x plus h times itself. And then this and that will cancel in the FOIL multiplication, getting a positive and then negative. And then minus root x times plus root x, that's a negative, but root x times itself is just x. Okay? All right, so I get that on top. On the bottom, I'll get h times root x plus h plus root x. Okay. Reduce just a little bit more. I see that the x's cancel. So I'll get h on top. H here. And that. And one more thing to reduce it, because I'm reducing it, right? I'll cancel the h's. So I get 1 with h over h. Root x plus h plus root x. Okay, so that's algebraically, that's how it reduces. Now I can apply the limit to this. Okay, so here's where the limit. In the beginning, I was trying to do the limit as h goes to 0. It didn't work on this given initial form, but I can now try it on that. Okay, so the limit as h approaches 0 of 1 over root x plus h plus root x. Okay, Is this different than that initial problem? Here, putting 0 for h gave me the form 0 on top, 0 on the bottom. Meaningless. That was just a cue to reduce it. Okay, so I reduced it. Is this any different? What if I can do the limit as h goes to 0 by putting 0 for h, by plugging in, substituting 0 for h? Then I don't encounter any problems at all. If that's a 0 right there, if I push the h all the way to 0, then I get that and that. Okay, so my answer. These are like terms. 1 over 2 root x. Okay. All right. So there, we did that one then. Kind of like the other one though. A little bit like the other one. Same thing with the conjugate. All right, so now what you see here is that, well, when we learn calculus, we might have to get a little bit better at algebra than we realized. But when you see me do these problems, you're seeing the kinds of techniques and things that you need to remember and be able to use.